So this is the exported detailing from ProtaDetails to AutoCAD, in which you can edit at your own pace and print for your use. Hi guys, this is Chevin Academy. Welcome back to our YouTube channel. In today's video, we are looking at design of cantilever retaining wall. Retaining wall has structures that are used generally to resist lateral pressure from the soil. So in this case, it is mostly used when there is a change in the ground elevation that is higher than the soil angle of repose. We have different kind of retaining wall. You can have gravity retaining wall, cantilever retaining wall, we can have counterfort, and we can also have buttress. So retaining wall are generally used in construction. For example, in dam construction, they are used in bridge abutment. They are also used in underground construction work or basement construction work. But before you can design a retaining wall, you need to understand the component and the loadings required or in which the retaining wall is subjected to. Looking at this diagram, you see the various components of a retaining wall. You see the stem, which is the vertical member of the retaining wall, the longer side. It is also called the arm. Then you can see the toe, which is the front part of the base, the heel, which is the lower part of the backward part of the base of the retaining wall. Then you also have the key. The purpose of the key is when the depth of the retaining wall is so high that it's become uneconomical, then you can provide key to reduce the depth so as to cater for the shear failure. Then this part of the retaining wall is the backfill, where you have the soil. So this part is called the active pressure. Then this other part is where the soil is. This other part is empty because the soil is here. We are trying to retain the earth on this other side. So what are the loads that can be applied, or what are the loads in which a retaining wall can be subjected to? So retaining wall, in design of retaining wall, you need to consider the following loads. We have the earth pressure, which is what the soil exerts on the retaining wall, which is on the arm. Then you also have the water pressure. This can actually come in two forms. So you are going to have the submerged pressure. This one is going to be computed from the submerged density of water. This is because of the soil submerged in water. Then you also calculate for the water pressure from the density of water itself. Then you have the surcharge pressure. Surcharge pressure are loads that are applied behind the retaining wall. They can be moving load or they can be permanent load. For example, when you have a retaining wall that retains earth, and above the retaining wall you have a road network above this retaining wall here. So in that case, the road network will be considered as a surcharge load on the retaining wall. Then the last type of load is the own weight, that is the weight of the retaining wall itself and the load of the earth. So now let's take a look at an example of how you can design a retaining wall of a stem height of 2.5 meters. Then it has a stem width at the top to be 125 millimeters, and at the base here is 200 millimeters. So we are going to run through the design of this retaining wall, and I'm sure you are going to get one or two things from it. Hello guys, so welcome back. To design the cantilever retaining wall practically, so we are going to be using the ProtaDetail software. ProtaDetail is a part of the software called protaStructures. So it is majorly for reinforced concrete design, detailing and analysis. So but we are going to be using the detailing part of the software, which is the ProtaDetails, and we are going to be using version 2018. So once you open the ProtaDetails package, so you are going to be having this pop-up that says open a project. You can create a new project but it's always better to start up using a already created project. That is, all the settings you have set for that project can actually be easily used for this. But if you want to create a new project, it is very easy. All you just have to do is just to click on this icon, new project, then you create your project. So I'm just going to say retaining wall as our new project, then click OK. Once I'm done, then you can now bring in your template. The template means, let me just say, like the design code you want to use, but template is just more than the design code. It also includes the project settings, which can include sometimes the diameter of reinforcement, the sizing, and all of that. So it's always better to use a project template. What this one means is all the projects you've done before is going to bring in their settings to this your new project. But because this is just a tutorial class, so I'm going to be using Euro code as my template. So the template for Euro code is the template for this video. Then you click on import. Once that is done, you give the software a little bit of time to load. Then we are now going to come to start by creating a new drawing. Click on it. Then you come to design library. Then you come to cantilever the retaining wall. This is what we want to design. So on the right corner or the right hand side of the software of this tab named retaining wall, you see we have different parameters. You have the geometry, you have the soil parameter, you have the analysis, you have the failure part, the design, and the drawing or report. So this geometry is where you input the geometry of your retaining wall, and which include the sizing and all of that. So once you are inputting the sizing, the software is going to be designing for checks like overturning, sliding, maximum pressure and the minimum pressure, or maximum stress and minimum stress. Then it's also going to be giving the accumulation here under total failure. The non-EQ means when you are determining for, let me just say, non-seismic load. EQ means seismic load in Euro code. So this one is case for non-seismic. In my own case, most of my design is non-seismic, but if you are designing in a seismic environment, you make sure that the other section under non for seismic environment are perfectly checked, that they are perfectly adequate. So the green color indicates that it passed the check, while if the color changes to red indicates that the check fails. So this is the geometry, or this is a sample of our retaining wall. In our own case, our own wall height is 2.5, but that is just the height of the stem. If you look at the diagram on the right hand side, you can see that h is the total height of the retaining wall right from the base up to the top. So but because we only have the stem height to be 2.5, so let's assume our base is 300 millimeters. So that means the total wall height is going to be 2,800, 2.8 millimeters. So then the wall length actually depends on the length in which the wall is going to extend. So you cannot see that from the section, but let's say our wall length is supposed to be 10 meters. That is, the cantilever wall is going to run through a 10-meter span. So you have a warning here saying that the wall height has changed. Do you want to use proportionate measurement for preliminary design? You can say yes. This one is like, it's going to give you a sizing that can work based on the height. So, or you can say no if you want to do that manually, but I will do that manually just for us to get what I'm trying to, how the software is going to design it. So change the length to 10 meters. Then you now talk about the stem top width. This is the stem, which is also known as the arm. So you can see that the stem top width is given as A, which is the thickness here. So from the diagram I showed earlier, we are assuming a thickness of 125, and then if you want to give this an eccentricity to the left, so if I change this to 20 millimeters eccentricity, you can see it dives away a little bit to the left 20 millimeters. So let me just give an eccentricity of 100 millimeters. Then the base plate front length, the base plate front length, this is the toe of the base, and the dimension is given as B1. So let's just use something like 400 millimeters as the base plate front length, or the same thing as the toe. Then we also have the stem width. The stem width is the thickness of the stem here. So from the diagram I showed earlier, it's supposed to be 200 millimeters. So once we change it to 200, as we are changing it, you can see that the design here are changing based on what we are inputting. Then the next thing is the base length at the back, which is the same thing as the heel. So you can input this to be something like 1 meters. Let's just check. So you can see once I put in 1 meters, you have some failure here. You can see that using a base plate back length of 1 meter will not be sufficient based on the seismic load condition. So I can increase it to maybe 2 meters. So increasing it to 2 meters will make this guy to pass. Then you now have the base plate slope angle. The base plate slope angle, it depends on the angle of your retaining wall. So let me just put in something like 15 degree. So when you put in 15 degree, you see how it's slanted, how the base of the retaining wall shifted a little bit. So I'm just going to leave it at 0 degree so that it's flat on the surface, it's flat on the ground. This is best for construction work. So then you can now come to the base plate. How do you want the base plate to form? Do you want to have it slopey just like the way we have it now, or you just want to have it straight? But if you have it slope, the thickness of concrete is going to be reduced. For example, you can see here is T1 here is 400, which is the total height. Then T2 is 300 here, while T3 is also 300. So but if you want to make it flat, the total thickness of the base is going to be 400, which is something huge. So making it slope will kind of reduce the thickness a little bit. So if you make it flat like this, then you change the base thickness to something like 300 and see if that will work. You see it works perfectly. It works perfectly. So let's say you want to provide key for your retaining wall after you've inputted all your parameters, and maybe the design is failing at the base, and because of that you need to add some additional weight, but you don't want to increase the thickness of the base plate. So in that kind of situation, you can provide key. All you just have to do is input the key parameters. Maybe in this case the width here is 500, the height is 400, the eccentricity is 100 millimeters. Eccentricity is from this base, then the K, if you want it to slope a little bit, that is what this K is trying to refer to. You see it slopes a little bit forward. So if I put it at 100 mm, it's going to slope more forward. So but for the purpose of this tutorial, I'm not going to be putting the key, so I'm just going to uncheck it. So let's say you want to add a parapet to your retaining wall. You can just check on this parapet. You see the parapet, you indicate the height of the parapet, the width, and if there is an eccentricity, you put the eccentricity. Then you also have shelf. This shelf is just to provide additional thickness for the base. So this shelf is provided like this. Yeah, you can put in the TS, which is the distance from the base. Then you can put in the BS, which is this from here to here. Then you can also put in the YS, that is the distance it has from the top to here. So that is how you can edit the geometry of your cantilever retaining wall using ProtaDetails. So let's say you are good with all the geometry, just like I am right now. Everything here is looking good. The overturning safety, the sliding safety, the maximum and the minimum stress. Then the next thing is to go to the soil parameter. So under the soil parameter, you have to edit the internal friction angle, the wall friction angle, the unit weight of the soil. So I'm going to leave that one as 18. Then if you have a saturated the saturated unit weight of your soil, and then if your soil is a cohesive soil, then you can easily check in and put in their values. Then here is where you can check for the soil bearing capacity. Using a soil bearing capacity of 200 kilonewton per meter square is something practicable for me, but you can easily change this based on your soil reports. Then this, we also have the base friction coefficient. The base friction coefficient depends on the soil type. So if you are having a silty sandy soil or a clayey soil, you can easily pick from here. You can see for the first item, which is the coarse sand and gravel with high permeability, the value is between 0.5 to 0.6. For silty sand or gravel with low permeability, the value is between 0.4 to 0.5. This depends on your soil condition. You can just pick from here and then you use. Then you come to the analysis tab. The analysis tab, here is where you are going to show what you want to analyze, and then the software, because you have been inputting the geometry, the software is designed in such a way that once is an automatic design. Once you change something, it do the calculation. Once you change another thing, it does the calculation automatically. So under this analysis settings, is just like showing you what the analysis looks like. So it gives you a summary of the vertical equivalent coefficient, the angle of seismic acceleration. You can see the passive static soil lateral pressure factor. You can see the overturning moment. You can see that the overturning moment due to static load is 45.8. Due to overturning, which is the seismic part, was 86.3. Then the resisting moment, for the design to be satisfactory, the resisting moment must be higher than the overturning moment. As you can see, that is what we have in this case. Then the same thing goes for the sliding force. The sliding force is 48. Due to the dynamicity, you have 78 kilonewton per meter. Then the resisting force is slightly higher than the sliding force. So that's why the design was satisfactory based on the sliding effect. So when you are designing retaining wall, you are actually designing the wall against overturning and sliding. So those are the two effects you need to check, the two paramount effects that you need to check. Then you now come under the total failure. Total failure will just give you the summary and the analysis of how they got this total failure of 2.31 greater than 1.5. Then you can now come to the design part. Here is where you can set, or you can see your design, which in other words we mean the reinforcement. So you can just come to the casting height. If you know that the total height of our retaining wall was 2.8 from the base, from the bottom of the base. But let's say you want to cast the retaining wall twice, so, and that is what is practically on site, because casting a height of 2.8 meters at once might not be easy. So you can cast it twice, maybe 1400, that is, you are casting it twice. So in that case, you need to provide something like a construction joint. You can see that the reinforcement stops here. Then you can now lap the other reinforcement to complete the casting. So then you can select your concrete type. So in this case, I'm going to be using C20/25. That's the grade of my concrete. Then the reinforcement as well, the rebar, I'm going to select Y12 and Y16. No, let me just use Y16 and Y12 and Y10 is okay for this. Then for the links, I'm just going to use Y10 only for my links. This is important so that when you run the design, the software will know the range of reinforcement to select. So once this is done, you can just click on the redesign. So when you click on the redesign, you can see what we have here. It's saying that the stem back face rebar is not sufficient because it's providing a diameter of 6 mm and spacing of 200. Probably there's a mix up here. So what we selected was 10 and 12. So let's select 16 mm and click OK. Then you click on redesign. So you can see selecting 16 mm, and then the spacing for this one is 140. So 16 mm at 140 is passing for this. Then as you click on each of the reinforcement, it's going to be highlighting the position of those reinforcements in the detailing. For example, when you click on the stem back face vertical rebar, you can see the highlight of the rebar. If you click on the next one, you see the highlight. So if you click on the distribution reinforcement, you can see them. The diameter is 10 mm and the spacing is 200 millimeters. So if you are good with this your design, all you need to do is now to come to drawings and reports. So under drawings and reports, here is where you are going to generate your report for the design. But before the report, you can see you can add other things like drainage details. That is, in the detailing that you are going to extract, you want the software to include a drainage hole, so you can specify the amount of drainage hole based on the diameter of pipe you want to use. So the drainage whip hole, in this case we are having 300 millimeters, 100 millimeters as the diameter of the hole. Then the spacing in which you are going to be having the hole, the intervals, is 1500 along the retaining wall. Then if you also want to use a drainage pipe, then you can choose the position you want to insert the drainage pipe. You have insert on wall far encasement or near wall far encasement, or on both. So in this case, let me just choose on both. Then you specify the diameter of your pipe. Let me use a pipe of 6 inches, which is 150 millimeters. Then one thing about the software is that it's going to give you the quantity of your concrete and quantity of your form work required. So from this, you can take this to your bill of quantities in order for you to quantify this retaining wall. So this is the volume of concrete, 18.75 meter cube, and the volume of, or the area of the form work needed, is 58.8 Newton per meter square. So if you don't want to include the quantities in your report, you can just uncheck this guy. But in my own case, I would like it to be included. So just check it and click on generate report. So the software is trying to generate the report, in which you can easily convert it to PDF and print it out. So this is your report. It names it at Cantilever retaining wall 1. You can rename it from here. Then you have the wall dimension, the soil parameters. You also have the analysis, the factor of safety, the surcharge load. You have the analysis, which is from the horizontal load, vertical load, the overturning stability, the sliding stability, the soil bearing capacity. Then you now have the analysis. So you see your reinforced concrete design. So this part is for the reinforced concrete design. You can see the reinforcement provided. This is the moment, this is the effective depth, the calculated area, the minimum area, and what was provided. Then at the end of it, you have the quantity measurement, which include your concrete quantity and your form work quantity. You can easily send this to, but if you look at this, you can see that there's a little bit difference from what we have earlier to what we have now. So this is because of the inclusion of the whip hole and the drainage pipe. So it's the software kind of remove those areas, so that's why you have a little bit slight difference between the two. So you can just send this to PDF by clicking on export to PDF, or you can just print if your laptop is connected to a printer. But this is just a tutorial, so I'm just going to close this. Then the next thing now is to generate our detailed drawings. So you can come to prepare drawings. Then you can just click on any part of the interface here. Then the drawing is going to be prepared. So this is the section. You can now see that under the detail, it has now included the drainage pipe, it has included the whip hole, and you have other information about the retaining wall. Then this is the slab, the reinforcement detailing of the retaining wall. This is each of the reinforcements. then this is the reinforcement call out, so that you can easily identify them, showing their shape and length. Then you now have the wall detail, that is the detailing of the wall. When I was doing this design, and I assume a wall length of 10 meters, so this is the length of 10 meters there. Then the next thing is that the software is going to prepare you a bar bending schedule, which is the quantity taken off, that's going to give you the total amount of reinforcement in kilogram that you need. You can easily convert this to tonnage to know the number of tonnage you need to buy in the market. So let's say you are good with this, you can extract this detail to AutoCAD and then put it in your back sheet and print. So to do that, all you just have to do is double click on this export dwg/dxf parts. Once you double click on it, you can change the directory where you want to save it, and you can also change the version of AutoCAD you are using. So if you are using a version lower than 2010, you can just easily pick 2004 DXF here, or you can make it a DWG file. So I'm going to retain the 2010 DWG format and then click on export. Once you do this, the software is going to export the drawing automatically and then open it where the drawing had been saved. Then you just double click on it to access it on AutoCAD. So this is the exported detailing from ProtaDetails to AutoCAD, in which you can edit at your own pace and print for your use. I hope you've get one or two things in this video. If you like this video, kindly hit the subscribe button, turn on the notification. See you in our next one.